We will continue with the membrane processes. As I mentioned, membrane market is very big. Globally it has become very fashionable and it is operated at atmospheric temperature. So membranes are widely used in water treatment, purification, removal of salts, removal of proteins. So both for purification as well as recovery or concentrating and various different applications. Several types of membranes varying from inorganic material of construction to synthetic polymers to natural polymers to composites and so on, and there are different types of membrane processes, ultrafiltration, microfiltration, nanofiltration, reverse osmosis, dialysis, electrodialysis, peroperation and so on. So a wide range of applications. It is going to replace as time proceeds many of the traditional chemical engineering processes. So we will continue today as well on the membranes, the applications and various the operating principles. If you remember this particular slide, we talked about the concentration polarization that happens because as the solution flows perpendicular to the surface of the membrane, there is a buildup of concentration of the solute in the upstream near the wall of the membrane material. So the bulk concentration of the solute will be much lower than the concentration near the wall, and sometimes these values may be 50% or 60% or even much larger than that. And the governing equation for this comes from the Fick's law of diffusion. So you have the flux is the amount that is flowing, that is amount of solute that is flowing per area per time is given by the diffusion coefficient D and dC by dx. dC by dx represents the concentration gradient along the distance. So x is the direction along the flow and D is the diffusion coefficient. The units are generally centimeter square or foot square or millimeter square per time, could be per second, per minute and so on. Now what are the boundary conditions? At x equal to 0, that is very near the wall in the upstream side of the membrane, concentration will be Cs, and at x is equal to D, D is your boundary layer, this is equal to Cb. So we have these two boundary conditions and it is very simple for you to solve. Now this boundary layer, as it is called here, this depends on several parameters. A typical chemical engineer can tell you what are the various parameters on which it depends. It depends on the liquid properties like viscosity, the density and the surface tension, and then it depends on the flow of the liquid near the wall. If the flow is turbulent, we are going to have a smaller diffusion distance or boundary layer. If the flow is very low, we are going to have very large boundary layer or diffusion thickness. Like last class I mentioned that you can create turbulence near the wall so that you can make the boundary layer much smaller, or we can even have cross flow. That means you can have the solution flowing parallel to the membrane plate rather than flowing vertical to the membrane plate. That way we can have much smaller boundary layer or boundary thickness. So if we solve that equation, you will get a relationship for the flux in terms of d by d. Now d by d is called the mass transfer coefficient, logarithm of Cs by Cb. Now this Cb is the concentration in the bulk and Cs is the concentration near the wall because of the concentration polarization. Okay, let us look at a simple problem. Imagine I am performing an ultrafiltration process and the rate of the process is 2.6 into 10 power minus 3 centimeter per second. The solution concentration is 0.448%. The diffusion coefficient for the solute is 9.5 10 minus 7 centimeter square per second. You note that the units for the diffusion coefficient is distance square per time, do not forget that, and the boundary layer is like this. What will be the concentration at the surface of the membrane in the upstream side due to concentration polarization? So this equation you substitute for D that is your diffusion coefficient. You substitute for boundary layer thickness small d, and then the rate is given, that is on the left hand side. So if you solve that, you will get Cs by Cb equal to 1.63. That means if Cb is 1, that is if the bulk concentration is 1, Cs will be 1.63. That means the concentration at the wall is 63% more than the bulk. That is a big number. So because of this concentration polarization, because of the build up of the concentration, sometimes the rate of filtration slows down, because there is a build up of concentration in the upstream. So you can see how much the concentration polarization is going to affect your filtration process. Now if your boundary layer is very small, that is boundary layer thickness is very small, it comes in the denominator. So if this becomes small, your rate will pick up. So that is our main goal, to increase the to decrease the boundary layer. Conversely, if you can increase the diffusion coefficient, then also your J can be made much larger. The permeate flux is given by a simple relationship. J is equal to L delta P. L is the membrane permeability, delta P is your driving force, that is the pressure. Okay. Now there is going to be osmotic pressure which will decrease this driving force. So in the presence of osmotic pressure, what will happen? The J will be equal to L into delta P minus S POS. P is your osmotic pressure, and S can be 0 or 1. If the solute is completely rejected, that means if the solute just passes through the membrane, then S will be equal to 1. That means the osmotic pressure will have an effect. If the solute is completely passed, then S will be equal to 0. If the solute is completely passed, S is equal to 0. If the solute is completely rejected by the membrane, then S is equal to 1. So if the solute completely goes through the other side, then obviously there is not going to be any osmotic pressure that is coming in the reverse direction. But if the solute is completely rejected, then obviously the concentration of the solute in the upstream will be much higher than the concentration of the solute in the downstream. So you are going to have an osmotic pressure taking place. Okay. So that will decrease your driving force delta P here. So osmotic pressure plays a very important role in reducing the driving force, and the property of the membrane process determines this particular reduction in the driving force. So if the solids are completely passed, then S will be equal to 0, because there is not going to be any buildup of osmotic pressure. If the solids are completely rejected, that means the upstream concentration of the solids or solute is much higher than the downstream concentration of the solids or solute, then S will be equal to 1. Then you will have maximum osmotic pressure effect on the driving force. So the driving force gets reduced. Let us look at a very simple problem. Now we are trying to do a purification using a membrane. The solute concentration is 0.1 mole. We are applying a pressure of 5 atmospheres. The reaction, the temperature of the process is 25 degrees. Now if the solute is completely rejected, that means the filtration process is so efficient that in the downstream there is no solute, only pure solvent will be flowing, and the upstream you have the complete solute. So if you remember, S will be equal to 1, that means you will have maximum effect of osmotic pressure in the pressure process. So equation becomes J is equal to L delta P minus POS. POS is your osmotic pressure. So you will have POS decreasing your driving force here, because solute is completely rejected. Now how do you calculate POS? Before going to that particular relationship, we will try to understand what is osmotic pressure and why does it arise and so on actually. Now imagine you have a chamber like this, and there is a membrane here. We have put in brine on one side, that means it contains salt, it is a salt water, and on the other side we have pure water. This is at time equal to 0. Now what will happen? Water will have certain vapor pressure, brine will have lower vapor pressure, because you have salt which is dissolved in water. So as you dissolve salt, there is a decrease in the vapor pressure, so the brine vapor pressure will go down, pure water vapor pressure will be high. So what will happen? There is an osmotic pressure. So the pressure, because of this, water will push it, and then water will enter here through the membrane, understand. So what will happen? This level will be higher, this level will be lower. Now this difference is called the osmotic pressure. So this difference depends upon the concentration of the brine solution, understand, and the operating temperature. Now if you want to make that water not to go from this side to this side, what do? We apply a pressure which is equal to the osmotic pressure. So by applying this pressure, we are forcing the water from the brine to the higher. This is called the reverse osmosis. So if you want to force water from a brine solution to a very dilute solution or to a pure water, we need to apply pressure much higher than the osmotic pressure. That is the principle of the reverse osmosis. Under normal circumstances, if you have a salt solution and if you have pure water solution, pure water, and we have a membrane, the pure water will diffuse into the salt solution because of the osmotic pressure, because of the decrease in the vapor pressure of the brine due to the presence of salt. So by applying that equivalent amount of pressure and more, we are driving pure water from the salt region into the pure water region. So this portion will get concentrated and concentrated with salt, and finally at some point the pressure you have to apply will be so high that you need to discard this particular salt water. And this is the principle in which even desalination of salt water works. There are now many places globally where pure water is produced using the desalination of seawater, especially in Middle East, many countries, places where we cannot have bore wells. There reverse osmosis is used for getting pure drinking water from seawater. So you apply very large pressures, the pressures are very high, it could be even 100 bars. So that is the main bottleneck in RO type of systems, the pressures will be very high. So your membrane system should be able to withstand that, and as time goes the concentration of the brine solution increases so much, you need to discard that brine solution and then you need to take fresh seawater. So when you discard the brine solution, you are creating environmental problem, because that brine solution is so concentrated with salt, nothing can survive there. That is the main problem actually. So a RO system has one big environmental issue, that is how do you discard this brine solution without causing any damage to the flora and fauna around. The next point is the operating cost. The membranes are very expensive, so from time to time you need to replace the membrane and put in fresh new membranes. So the membrane cost is also very high in RO systems. But then if you do not have drinking water, if you do not have rains and lakes, then you need to resort to this particular technique. RO membranes are also used in industry at the end of the wastewater treatment. If you are interested in getting potable water from a little bit of effluent, that means the effluent might not be very toxic effluent, but it may be slightly drinkable. So potable water is also prepared in RO membrane. So you may have a ultrafiltration membrane a priori, and then finally you may have a RO membrane, and then the water can be recycled and taken inside for gardening and so many other purposes actually. So that way RO has become very important nowadays, because if you are thinking about zero discharge in industrial setup, then this is the final ultimate solution. Okay, now let us go back to our old RO system. In reverse osmosis the pore sizes are very small. Okay, you can see the size is 0.0001 micron. So generally it permeates only water. So it does not allow salts and low molecular weight material to permeate through. So why do we call reverse osmosis? As I mentioned in the previous slide, we are applying a pressure in the opposite direction to the osmotic pressure, that is why it is called reverse osmosis. So in the normal osmotic pressure the solvent will diffuse from the low concentration to the high concentration side, whereas in reverse osmosis the solvent will be forced from a high concentration side to low concentration side. So the pressures as I mentioned before can even be 100 bar here. So it is very applicable for low molecular weight products such as salts, desalination of seawater, sugars, organic acids from aqueous solution. It is used in food and dairy industries to concentrate fruit juices, because if you have fruit juices we cannot go to distillation, and distillation will spoil the flavor and the taste of your fruit juice. We cannot go to solvent extraction because there could be residual solvent left behind and the solvent could be toxic for consumption. So the best approach is using reverse osmosis. Okay. So it can be used for fruit juices, it can be used for vegetable juices, for milk. Now if you look at nanofiltration, nanofiltration is much finer when compared to say micro or ultra. It is almost similar to reverse osmosis, but the membranes are slightly more porous and it can be used for separating molecules up to 500 Dalton. Okay. So in nanofiltration we can have still some molecules passing through, but in RO you are not going to have any compounds passing through, only the solvent passes through. So the solvent molecules pass from a region of low concentration to the region of high concentration. In osmosis what happens, the driving force for the flow of the solvents is the difference in the chemical potential. Okay. So we have a difference in the vapor pressure, so there is a difference in the chemical potential, that is what is called the osmosis. So when it reaches an equilibrium the chemical potentials have to be balanced on both sides, all the osmotic pressure needs to be balanced on the both sides. So the equation for the osmotic pressure is given by the Van 't Hoff's relation, that is called the osmotic pressure is equal to R, this is your gas constant, T temperature in Kelvin, C is the concentration of the solute per meter cube. Actually this is a simplified version of the equation because you will be having logarithm and so on actually. This is generally valid for dilute solutions, please remember, that is why we got a very simplified equation, otherwise you will have logarithm. When you have very concentrated solutions the actual osmotic pressure will be less. The ratio of the actual osmotic pressure to the calculated value is called the osmotic coefficient, or also it is called the correction factor, osmotic correction factor. So if you have ionic solutes you are going to have some dissociation taking place, ions, more ions may be formed starting from a single neutral molecule. So we need to consider the number of ions that are produced also. So you have the osmotic pressure equation slightly modified like this, N into R into T into C. N is called the Van 't Hoff factor, number of ions produced when the solute molecules completely dissociates. Now if you have more than one salt, so salt 1 can have one concentration, salt 2 can be another concentration, salt 3 can be another, then you are going to have summation of pressure caused by each of the salt. So the total osmotic pressure will be the summation term here, and C here can be concentration 1 of salt 1, then you can have plus concentration 2 of salt 2 plus concentration 3 of salt 3 and so on actually. So it is an additive property if you have more than one salts. So this particular term will lead to a decrease in your driving pressure. Now if you go back to your old problem, we are talking about the solute completely rejected, so what the S here became 1, so J will be equal to L is your permeability, delta P is your pressure, POS is your osmotic pressure. Now POS is given by RTC, C is given by 0.1, T is given by 25 degrees centigrade, that means 273 plus 25 298 Kelvin, R is your gas constant. So that will give you the POS. So you know POS, your pressure may be 5 atmosphere, but because there is a negative term and POS comes in, your total driving force gets decreased. So your rate in the membrane is decreased because of this R into 298 into 0.1, understand. So this is how you calculate the rate of membrane purification. There are different types of membrane configurations which I mentioned yesterday. You can have a flat sheet membrane, that is like a plate and frame design. We can have a spiral wound membrane, that means the membranes material is wound like a spiral, so the flow also takes place in a spiral fashion. We can have a tubular membrane, that means it is like a tube, and the tube is, the walls of the tubes are porous. We can have hollow fiber modules, it is like a shell and tube type of system. So all these types of designs are possible. The whole idea is to increase the surface area of the membrane per unit volume minimal. If you go to flat sheet membrane, the surface area per unit volume is low, whereas if you take the other membranes, the surface area is much higher. Okay. So these are simple schematics of these different types of membranes. So you have a tubular, you have a long tube, the walls are made up of membrane material. As I said, it could be a organic material, it could be a natural material, it could be a composite. So your slurry flows in and the solvent flows out through these walls, and you may be getting concentrated liquid. If you look at this, this is a plate and frame design. So surface area per volume is low here, you have the membrane here, slurry flows in. So if I want to increase the surface area, I will put many plates, that is the whole idea of this. If you look at the shell and tube type of situation, we have lot of tubes. This is like a heat exchanger, shell and tube heat exchanger. You have lot of tubes, so you have a header here on this side, you have a header here on this side. So your slurry flows in, it gets distributed into various tubes, and then finally the concentrated liquids again are collected from all these tubes into the header and then removed. So this is a shell and tube design. So if the one of the tubes gets spoiled, we will open it, we will remove the tube, we will put in another tube. So this is how you perform the process. Tubular membrane. So it is called a shell and tube module. It consists of several tubes of membranes bounded at each end, that is a header, and again on the other side also you have a common header. So the slurry flows in, gets distributed, and then the permeate passes through the wall, because the membrane walls are porous. So the retentate passes out on the other side, again they are collected at the header and then removed actually. So where do you use? If you have very high viscous feed material, or you can have, mostly high viscous feed material is in either food products or is it in fruit juices. Example is like a tomato puree, where you want to concentrate it to a very high degree. So the water will pass through the walls and come out, and the tomato puree, which is very highly viscous, will flow through the entire tube. Hollow fiber, we have the hollow capillary fibers of membrane packed into a shell and tube arrangement. So you get a very high surface area per unit volume. Here the feed must be free from particulate matter, otherwise what will happen, if there are any particulate matter, it will go and get stuck to the hollow fiber, it will do a mechanical damage to the fiber, or it will even prevent your filtration process. So what do? We may have a pre-filtration facility. So you may have a ultrafiltration in the beginning and then you may go to a hollow fiber membrane. So if you have a ultrafiltration, then in the hollow fiber the pressure is applied on the inside of the fibers, okay. So that is the driving force. But if it is an RO process, then the pressure is applied on the shell side, that means it is applied on the outside. Hollow fiber is preferred in dialysis because we are looking at very large surface area and we do not want to apply big driving force also, because we are dealing with the human system, the driving force is not large like an industrial scale. So the other idea, other way of increasing your flow rate or the filtration rate is to increase the surface area. So hollow fibers are preferred in such a situation. Microfiltration, now this resembles conventional filtration, just like a normal filtration process which we studied many classes back. So the filter medium is a porous membrane, so it can be used for filtering particulate material, so big material. It can be used for suspended solids, so it cannot be used for dissolved solids. So microfiltration is almost like a early stages, instead of a normal filter cloth we can even resort to microfiltration. So dissolved solids cannot be separated in microfiltration. So we can be used for harvesting microbial cells. So if I am interested in intracellular material, I can use a microfiltration from fermentation broth. I can use it for separating blood cells and plasma from whole blood. So what type of configurations do you adopt in microfiltration? We can go for plate and frame, we can go for spiral wound, we can go for hollow fiber module. So all these types of designs are possible in microfiltration. So we have thin and porous filter medium or membrane supported on rigid support, it is not like a normal filtration system. So we can have synthetic organic molecules like polypropylene or PTFE, we can have alumina or zirconia, and they have to be made chemical resistant if you are processing chemically active solutions. The most important points we need to consider is the wettability, because the membrane should not be very hydrophobic, otherwise wettability will be very poor. Absorption characteristics, will the membrane material absorb salts, because if it absorbs and starts swelling then that will be a problem. The chemical and mechanical stability, it should be chemically inert, otherwise we do not want any reaction taking place with the solution and the membrane. It should be mechanically stable because we are applying pressure, sometimes you may have solids which may be causing attrition to the membrane surface, so it should be mechanically stable. In most of the membrane process, the cost of the operation is determined by the cost of replacement of the membrane. So membrane cost is the highest, which makes or breaks your operating cost in a membrane process. So here we can allow even macro solutes, but not colloids and suspended solid particles in the size range of 0.1 to 10 microns. So the flow of solvent and the solute is because of the convection through the pores. So it is like a normal sieving or filtration process. The pressures are low, 1 to 2 bar only. So we can operate in a normal flow mode, that means the solution flowing perpendicular to the membrane surface, or it is also called dead end method, or it can be cross flow mode. The normal mode, the feed is entering perpendicular to the filter medium, So as the filtration progresses you are forming a cake, so the cake formation will decrease your rate of flow. We talked about cake and resistance of the cake and so on long time back. So this is a typical place where those issues will come into. And if you are using for the separation of biomolecules or microbial cells, the cake could be compressible as well. So if the cake is compressible, so there is going to be a nonlinear relationship of the flow with the pressure drop. I hope you can recall those equations which we talked about a long time back. So the flux here will depend upon the driving force delta P divided by Rm plus Rc. Rm is the resistance of the offered by the membrane and Rc is the resistance offered by the cake. The pores in the filter medium are small, so the filter medium also will offer some resistance, unlike the normal filtration. In a cloth type of filter, the resistance offered by the cloth is much smaller than the cake, so we generally neglect it. But when you are talking about this type of filtration, microfiltration, the pores are slightly smaller, so we need to consider that also. We cannot totally reject that, so keep that in mind. Now the resistance offered by the cake, if you recall our old Darcy's law, this is the equation, and delta P raised to the power S because of the compressibility of the cake. Okay, A is your area. So alpha is your specific resistance, W is the slurry concentration, dry solids per meter cube of filtrate, S is the compressibility, so 0 for incompressible, okay, or 1 for perfectly compressible. So you can have values varying from 0 to 1. V is your total volume of the permeate, N is the viscosity of the permeate, A is the area of the membrane. So because as I said the membrane material will also offer some resistance because the pores are much smaller when compared to your traditional cloth or CU or metal type of filter in it. So we need to keep that also here. So this is a typical equation. If you recall from our very early classes, the flux is given by all these parameters. So S can vary between 0 and 1. So if it is incompressible, this term will completely disappear. If it is fully compressible, you are going to have S is equal to 1 also. Okay, so the S can vary between 0 and 1 depending upon the compressibility of your cake. So of course if we assume that the Rm, that is the resistance offered by your membrane material, is very small, we can neglect that. Okay. Now in many cases alpha, W, eta and the total flow rate through the membrane are always constant actually. Okay, we can assume. So once the flow rate starts decreasing because of the compressibility of the cake, maybe you will stop your filtration, you may do a back flushing or you may do a dismantling and removing the cake that is formed, and again you will restart your membrane. This is like a traditional filtration, that is regenerating your membrane filtration process. Now the disadvantages of microfiltration is frequent fouling. So you are going to have fouling because of the settling of the cake. So we need to from time to time do a back flush and remove that cake that is formed. So you may be a filtration process, back flushing process, that is cake removal, again filtration process, back flushing and so on actually. So ideally you would like to have a very long filtration without actually doing a back flushing, which will slow down your overall rate. So once the pressure keeps increasing slowly and slowly because of the deposition of the cake, the membrane needs to be either cleaned or replaced. Sometimes the membrane gets totally compacted, so even if you do a cleaning you will not be able to recover its permeability. So at that point you may have to replace your membrane material. Now increasing the area of membrane twice decreases the flux by half, okay, but total volume of the filtrate will increase 4 times. But increasing the area of the membrane will reduce the membrane replacement cost by half, okay. So the question is, do we have very large area membrane? So if I want to have very large area membrane, that means my capital cost of the membrane setup will be high, the cost of the membrane itself will be high, but then replacement cost will go down. That means I will be able to do the filtration for much longer periods of time. That means the operation, that means the plant will be running uninterrupted for much longer time. So you need to balance between, should I have a big membrane assembly with the large surface area membranes, or should I have smaller assembly, that means my capital cost will be less, but then I will be doing the membrane cleaning or membrane replacement quite frequently. That means my process will get disturbed much more. So can I afford to do that, or do I need a big plant where I will have a much larger surface area membranes, then I will be running my plant undisturbed for much longer periods of time. So you need to balance between your real process and whether you can have more stop start, or you want to have uninterrupted type of operation. So that all depends upon what is the product you are manufacturing, what is the fermentation that is taking place, what is the fermentation time, and so on actually. So if your fermentation broth can be stored in a tank, intermediate tank, and then you can do a filtration in a membrane process, so that your fermenter is not disturbed when you stop and start your membrane filtration, then you may be able to afford to have a smaller membrane unit with lower surface area. Whereas you cannot afford to store your material after fermentation, but you want to quickly do a filtration because maybe the biomolecule or a bioproduct is very sensitive to the salts present or the toxins present that you want to quickly filter and recover, then in that case you will not be able to store it, but you want to you will not be able to have too many start and stop. So in that situation you will like to have a large membrane assembly, that means you will have a larger surface area membrane as well. So the buildup of solids on the membrane can be minimized by installing a depth filter upstream. So we can have a pre-filter or a depth filter. I talked about depth filter also before. So that depth filter will remove a large amount of quantity of your suspended solids, and then we can go to a membrane. So the buildup of cake in the membrane will be much less. Another disadvantage of microfiltration is concentrated slurry and not a dry cake. So you will not get a dry cake, the pressure you are applying is only 1 to 2 bar. So the buildup of solid will be more slurry rather than a dry cake. That means the slurry again needs to be processed if you want a dry cake. That means we may have to take it to a oven or a dryer where we remove all the solvent or water, and then you get the dry cake which can be disposed of. As the filtration takes place, you are also going to have the increase in viscosity. That is another problem in microfiltration. So the viscosity of the slurry as the solvent is removed is going to increase, so it will retard your permeation or membrane filtration process. So these are some of the disadvantages of this type of filtration, microfiltration. So if you want to keep the rate of filtration high, we have to keep on increasing the pumping to sustain the cross flow, okay. So sometimes we may go into microfiltration followed by conventional filtration or even centrifugation to separate the solids completely. Now let us go to ultrafiltration. Now ultrafiltration, the pressures are slightly higher. So in microfiltration we are talking about 1 to 2 bar, then goes to ultrafiltration where the pressures are around 2 to 10 bar. So separation is based on the molecular sizes. So it is very useful in separation of high molecular weight products, polymers, proteins, colloidal materials from low molecular weight solutes. So I want to separate out proteins and also have some low molecular weight solutes. It can be used for concentrating and clarifying fruit juices. That means we can concentrate fruit juices. As I said, we cannot use distillation here. We can even clarify fruit juices, because when you prepare fruit juices you may have suspended matter which will spoil the appearance of your fruit juice. We can use it for recovery of whey proteins when you are manufacturing in cheese. We can use it for concentrating cell free fermentation broths containing monoclonal antibodies. So that means I want to remove whatever cells that are still left behind during my conventional filtration or during my microfiltration, then I can go to ultrafiltration. So this comes as a second step in my filtration process. So the material of construction, we can have polysulfones or other polymers, it can have finely made microporous, and the pore size could be asymmetric also. So this pore size is much smaller than microfiltration, pore area per unit surface is also less, so the flux will be much lesser when compared to MF. So the liquid flows through the membrane because of viscous flow and you are applying moderate pressure here. The osmotic pressure is negligible in microfiltration when compared to RO or when compared to nanofiltration, because you have high molecular weight of the solutes. Okay. So the microfiltration operates more like a viscous flow. The flux in ultrafiltration is reduced due to concentration polarization. Okay. Because slowly the solids are going to get accumulated, the solute is going to get accumulated in the upstream at the surface of the membrane. So the flux starts decreasing. Okay. We cannot keep on increasing the pressure drop, because again that depends upon your membrane characteristics. So here also you are going to have a incompressible gel layer formed because of the concentration polarization, and if you remember the concentration polarization equation is J is equal to K logarithm G by Cb. Okay. Now K can be called a constant, or it is made up of a diffusion coefficient, it is made up of a boundary layer and so on actually. So J is independent of pressure drop, because J depends only on the diffusion coefficient. Now we have only diffusion coefficients coming into picture, the boundary layer coming into picture, the concentration in the bulk and the concentration of the gel or concentration at the polarization layer comes into picture actually. Okay. Now J is independent of pressure drop. Now rate of loss of solute will be equal to solute flow through the permeate. Okay. So what we have is dVc by dt is equal to J into A into Cp, okay, or dVc by dt is equal to JAC into 1 minus R, where V is your retentate volume, C and Cp are the concentration of the solute in the retentate and the permeate, A is the area of the membrane, R is the retention coefficient. Okay. So R is your retention coefficient, A is your area, Cp is the concentration of in the permeate side, C is the concentration in the solute in the retentate. Okay. If the retention coefficient for a solute R equal to 1, then Vc will be a constant. Okay. Vc will be constant here. So because 1 minus R will become 0. If R is less than 1, then we can take out C outside and then have dV by dt, or we can take V outside, then it will become dC by dt. This is equal to JAC 1 minus R. This is for R less than 1, that is the retention coefficient. Now dV by dt can be replaced by J into area. J is your flux, A is your area, okay. Okay. So what we have is an equation here. This equation tells you how the changes in the filtration rate or how the changes in the concentration affect your flux on this side, okay. That is what this particular equation tells you, and this equation is valid if R is less than 1. If R is equal to 1, then we will be neglecting that part. So you see, in ultrafiltration the concentration polarization plays a very important role, whereas in a microfiltration it is more like a normal filtration process where the compressibility of the cake plays a very important role. So there we are not talking about any concentration polarization, there buildup of cake, it is like a normal filtration process using a cloth or a metal sheet or something like that. But here the concentration polarization and buildup of the solute which forms a gel, which will slow down your rate of filtration. As the gel concentration keeps increasing, the rate of filtration also keeps decreasing. So as the gel layer increases, again the rate of filtration also keeps going down. So at some point we need to either remove this gel layer by doing a back flushing, and beyond some point we may have to replace the filter medium itself. That means we need to replace the membrane material itself to bring your rate of filtration to its desired or normal value. So these are the two main things that happens when you are talking about a microfiltration and the ultrafiltration. So we are going to use quite a lot of solute, okay, and during this ultrafiltration process because of the concentration polarization, and the solute does not diffuse in through the gel layer or the concentration layer, okay. So we will continue on this further in the next class.